Hi everyone, welcome to this M2D2 talk. Um, our speaker today is Xiang. He's a PhD student at MIT CSEL, advised by Tommy Yakola. He's interested in learning generative model and dynamical model for multi-scale molecular system. His research centers around accelerating molecular dynamic simulation and generative model for material design. Thank you so much, Xiang, for presenting your work with this group here today. And for everyone in the audience, if you have a question, please write in the chat or raise your hand and then when the time is right, the speaker will address your question. Thank you so much.
Thank you, Prudence, for the introduction and for the invitation. I thank everyone for coming here to so I can share my research with you. So I want to say a few words about machine learning for multi-scale molecular simulation and design. So the focus today is on the multi-scale part. There are many new papers. It's becoming very popular as a machine learning sort of subfield for AI for science and molecular modeling. However, there are many motivations, good motivations, that we may have for using a multi-scale modeling approach. So the nature of molecular systems is multi-scale. So you have, from the best to our understanding, from the most basic particles, they form atoms, and then they form molecules, and then so on. So there's really little hope to model something as complicated as a cell with the ab-initio accuracy. It sort of necessitates the approach of using a multi-scale learning approach when you are dealing with increasingly complex systems. With machine learning, we can do multi-scale modeling of molecular system with spatio-temporal coarse-graining in order to enable large-scale simulations. We can also enable multi-scale design by generating materials or molecules with hierarchical structures. Today, I'm going to present our recent works on both sides of the multi-scale machine learning for molecular simulation and design, these two aspects, to demonstrate how coarse-graining and multi-scale modeling plays a role for us to help in order to enable us to model big systems and to design big systems. So the first paper that I'm going to spend some time discussing is simulate time-integrated coarse-grained molecular dynamics with multi-scale graph neural nets. So the motivation for this paper is we want to enable fast molecular dynamic simulation. So these complex systems are often very big. They involve like 10 to the 4th to 10 to the 7th atoms. So this number is taken by, if you look at the biggest O-atom simulations today, that's roughly sort of a range where people would say these are very expensive. Like if you're simulating a protein chain in a solvent, it's roughly at the order of 10 to the 4th. And the biggest system nowadays people simulate are something like a protein condensate or something like a huge bulk materials that can be up to 10 to the 7th atoms. So with this number of atoms, it's imaginably the system simulation is going to be very expensive. You also need very long simulations to probe some of the most interesting properties of a system. For example, on the right-hand side, what I'm showing you is a picture of a polymer lithium electrolytes. And for this electrolyte, you have lithium ions travel within these materials. And what you care is, because you're trying to use it as an electrolyte in a battery, you want the lithium ions to travel fast in this material. So to measure how fast the lithium ion travel, you will need to first enter the diffusion regime. That means if you think about the lithium ion within this materials, the lithium ions will try to diffuse within it. However, it has all these polymer chains wiggling around. So the lithium ion will move, but it will like hit the polymers and then get reflected back. So it will have this random walk like behavior if you only try to observe a short timescale. And you can only reasonably measure how this material is going to perform in a realistic scenario by simulating the system for long enough so that you will see the lithium ions, like to get the actual travel distance of the lithium ion within a certain time window. So this necessitates long timescale simulations. So the similar concept is also in, say, proteins. A protein, they fold and they may unfold, and they may just transition from different modality of conformation. So this does not happen very quickly. If you know a famous paper that people use a lot is a paper called how fast folding protein folds. So this paper investigated a few fast folding proteins. These proteins fold very fast. However, they still take hundreds nanoseconds or even to microseconds to reliably observe these folding and unfolding events. So these long timescales also makes the simulation so expensive, and the sequential nature of these sampling process also make it so long time for you to you need to spend so much time, not just compute. It's not even parallelizable sometimes for you to get these trajectories. And oftentimes we're also dealing with large chemical space to simulate. So on the right-hand side, again, we are looking at the polymer electrolyte, right? So this polymer electrolytes, maybe our goal is to find a better one. So today, our batteries are still dominantly using liquid electrolytes. So there are many advantages of solid polymer electrolytes, which include safety, for example, because you no longer need to hold some liquid in your cars. So people like these solid like as a research area, people are interested in these electrolyte for some reasons, but they are not good enough. So the focus is still to design better electrolyte like this. And for us to design, we will need to propose many possible conformation, like many possible potential polymers that we may want to use as an electrolyte, and we want to have many of them. And when we want to screen all of them so that we know which ones are better and should we proceed to the next step, maybe synthesize them. So you will need to screen many, many different polymers. And each of them will take like 50 nanosecond simulation, and each of them contains maybe 10 to the fourth atoms. So you not only need to run very large scale simulation, very long simulation, you also need to run many simulations for many different systems. So all these challenges come together, gives you this hurdle for you to do scientific research with molecular dynamics simulation. It's really costly to run these simulations at an ideal level of scale, length, and broadness to actually achieve a meaningful scientific goals. So the motivation for our recent research is to accelerate this process. So it's such an important problem. It's such a general problem. So there are many past efforts, or there are actually still existing very popular, very active research areas. So I will just briefly introduce some existing approaches. The first, I would say, is enhanced sampling methods, where you will bias the potential energy surface so that you can sample different conformations very more efficiently. There are also traditional coarse-graining methods, where you will define coarse-grained beads, and you usually define these coarse-grained beads or coarse-grained configurations based on chemical intuition from and the features of the original atomic system. Usually, so these are combined with coarse-grained force field oftentimes, and you can also machine learning these coarse-grained force fields. We also have machine learning force fields here. I put it here as a single topic because it's such a very vibrant research area. And oftentimes, it's the most prevalent for this method to work when your reference data was ab-initio accuracy. So that is, for example, if you use DFT to compute some energy and forces for a system, every single calculation is very expensive. So for the solid polymer electrolyte systems that I presented just a few slides before, you don't even use like quantum mechanical force fields to simulate a system like that. It's too big for a DFT-based simulation to work. And you don't know how well it will work, because DFT simulation is often meant for smaller systems and for shorter timescales. And for those types of simulation, we know they are very, very accurate. However, they are so expensive. And machine learning force field has made huge progress in that you can recover the ab-initio accuracy, but at a cost that's orders of magnitude smaller. However, the focus of this work and the simulations we're cared about are often carried out by classical force fields. So these are the scenarios where DFT is too expensive, and we're using a very efficient classical force fields to get the reference trajectories, or we're trying to accelerate over already very fast classical force field simulation. And in this case, machine learning force field often does not have an advantage, because the classical force fields are often defined in very simple functional forms, and they are very fast to evaluate. So a machine learning force field is rarely as fast as some simple equations like that. So the last realm that I think is relevant to accelerating MD is machine learning generative models. So for example, this past work called Boltzmann generator is a normalizing flow model where you can try to flow from a Gaussian distribution to the Boltzmann distribution of molecule. So this types of work, they achieve impressive results in certain scenarios, such as an alien dipeptide molecule. However, one drawback I would say is they don't capture the dynamics well. So, for example, previously we chat about the solid polymer electrolytes. We're trying to look for the systems, the materials where the lithium ions travel fast in the system. So that is a dynamical property. You have to have a timed trajectory to measure that. However, if you're using a normalizing flow and trying to get the Boltzmann distribution for that, you will not get any dynamical information out of such a distribution sampling. So this is more useful for you, for example, if you want to study the conformation of a protein, but it's not enough if you're trying to study, say, the folding timescale of the protein. How fast does this protein fold? After how long will this protein fold once? Like, how stable is this thing across time? So when it comes to time-related properties, it's hard to study with machine learning generative models. So we here characterize two potential like drawbacks of this existing method. They either only capture equilibrium distributions and does not provide dynamical informations, or they may not be fast or accurate enough for many real-world MD applications, such as the battery stuff we just talked about. So now let's look at some ingredients that we may use to extend the scales of molecular dynamic simulation. So we know these systems are complex. They have thousands of atoms, or even tens of thousands, or even millions. So the way to go with this is to consider spatial coarse-graining to reduce the number of atoms. So this is often okay, because if you want to study the protein fold or unfold, you don't really care if this carbon-hydrogen bonds, how fast they vibrate. So this doesn't matter if you're trying to think about how fast a protein fold. And for this lithium-ion battery, it also doesn't care so much about how this polymer chain wiggles, especially the details like this carbon-carbon bond or this carbon-hydrogen bond. They don't matter. And we also need to deal with very long simulations like nanoseconds or microsecond level. So how do we deal with this? If you're using a force field, because the force changes so fast, it's a very rock energy landscape if you think about it. So you often have to use a very short time step if you want to integrate this with a, say, velocity-related integrator. So these potential-based force fields if you want to simulate it, you will have to take very small time steps at the level of like 1 femtosecond or 10 femtosecond at most for some coarse-grained scenarios. So by the way, a femtosecond is 1 to the 10 to the negative 15. And so how do we deal with this? And the natural thing come to my to one's mind is maybe I want to enlarge this time step. And when you enlarge these time steps, you almost surely cannot use a force field never like anymore. So all these defined classical force field or machine learning force field, TFT force fields, all these force fields are defined with a very raw energy landscape, and there's no way to integrate these force fields with long time steps. You cannot go to picosecond level or further. So a common practice in this work and in several previous work regarding latent space MD simulation uses a long time step at picosecond or even nanosecond level. So we also have a large chemical space to simulate. So we will consider, what if we learn the simulation, we learn the simulator, or we call a propagator in this case, from short MD trajectories, and then we can use our simulator to simulate long trajectories for novel unseen systems. So this is possible because the evolution rule doesn't change, whether it's a long trajectory or short trajectory. So the knowledge contained in short trajectories are the same as if they were as in the long trajectories, because you are now trying to predict chunks, very long-term futures. If you are trying to learn a simulator, you are really just trying to, in this case, predict the next step. And if you just predict the next step, as long as you have enough line, you have like reasonable length trajectories for you to start trying to learn, it's enough. So in our case, for example, for the polymer electrolyte stuff, we train with trajectories that are 5 nanosecond long, and we test them on 50 nanosecond simulations. And this is nice. Why? Because now we can parallelize the compute by having many short trajectories simulated in parallel with many CPUs or GPUs. If you do have the resources, you don't need to wait like after a month for you to get all the like a very long trajectories done for that molecule or for that protein, but rather you can just simulate many trajectories at the same time, so that your machine learning model can learn from all these data to get a sense about how to simulate. And then your machine learning simulator is fast because it's coarse-grained. It also has a long time step. So now you can very efficiently simulate very long trajectories with machine learning model. So let's see how we combine these ingredients in this paper. So here I'm showing you this fine-grained structure of a single-chain polymer. And this polymer has this many beads, like 1,000 beads or so. And this seems like a relatively complex systems. If you are familiar with what kind of system that machine learning force field often deal with, they are like MD17, MD22. These systems often at most contain like several hundreds of atoms at most. This is a complex system, I would say. And we can first do a graph clustering to assign a coarse-grained mapping. And then we will group all the atoms into coarse-grained beads for each of the atom group. We can also then extract or construct the coarse-grained bead features. For example, the position of the coarse-grained bead will be the center mass for the all the atoms in that group. And the weight of the coarse-grained bead will be the sum of the weights for the atoms. And the type of the coarse-grained bead will be the mean of the atoms in that atom group. So we can do the same thing for all of these polymers, for different polymers. It's a consistent way to construct a coarse-grained representation for all different types of polymers. So this is how we coarse-grain the system. We can coarse-grain this polymer chain into only 10 beads. And for this more complex polymer electrolyte system, we can coarse-grain like 10 to the 4th atoms to 10 to the 3rd, 10 to the 3rd. So the hope is, after you do the coarse-graining, you can still preserve the key properties that you're interested in. And this is often a hard question to answer. So when do I lose the actual property that I care? So at least in this work, we didn't really answer this question. We'd rather just find a reasonable enough coarse-grained level, and it turns out they work. But this is a very important question that is hard to answer, and I think it's a very promising avenue for future work. Prudencio.
Yes, so how do you determine the cross graining here? How do you know if 10 beads is enough instead of 20 or 100 beads?
Yeah, so here for these systems, we do know what we care about. We do know for these polymers, we care about like how much they sort of what's the compactness. So the compactness means how they wiggle around, like how would they like just compress into very condensed blobs, or are they very extended like a chain flowing around? So if we know that's what we care, we will try to just scan a few coarse-grained level to see at which level we preserve this property well. And for the polymer electrolytes, we care about the lithium-ion diffusivity, like how fast the lithium-ion travel. So again, we're using how well can we predict these key properties as the guidelines for how we select a hyperparameter. So the hyperparameter is how much we coarse-grain. I understand this may not be the most ideal thing to do, but it really depends on what kind of behavior or what kind of phenomenon you're trying to investigate to decide how much you coarse grain. For example, many protein coarse grain simulation, they would see every amino acid as a bead, or some more informative ones will see, okay, I have the backbone carbon as one bead, and then have a side chain as another. So if you look at even more large-scale simulations, such as some simulations at U Chicago, they investigate how the HIV capsid form. So it's the capsid of virus. So in that case, it involves so many proteins assembled together to form a virus capsid. In which case, it will group maybe 10 amino acids into one bead. So the granularity of the simulation often highly depends on what kind of phenomena you're trying to investigate. And we are lacking a theory on how to decide what is the right granularity for what I care.
Perfect, thank you.
Yep. Okay, so we are dealing with the complex system with a spatial coarse-graining approach. We haven't talked anything about, okay, the simulation is still long. Okay, you've reduced your number of atoms from 10 to the 4th to 10 to the 3rd. You still need to simulate for 50 nanoseconds. So how do we deal with this? We want to use very large time integration steps at nanosecond level without force computation, because once you use force, it necessitates a very short time steps. So we are looking at this MD trajectory, and it was simulated at the femtosecond level time steps. And we just did the coarse-graining approach that we just mentioned. We get a coarse-grained trajectory that are evenly spaced with femtosecond level time steps. What we will do is we will downsample this trajectory to model a time-integrated dynamics. So after the downsampling, you will see, okay, now each frame, there is maybe 0.2 nanosecond in between, or like a few hundred picosecond. So this time integration effect gives you this diluted trajectory, which I aim to learn with a machine learning model. There's no way you can get such a trajectory without like this short time step integration if you're using a traditional method. But with machine learning, I really hope I can learn somehow how the system evolve at this large time scale. So the last ingredient is we have a large chemical space to simulate. And we aim to learn from short MD trajectories and simulate long trajectories for novel and unseen systems. To do this, we consider our machine learning simulator. It operates at a coarse-grained level, and it learns to simulate the time anyway dynamics. We have this large chemical space that we want to screen over. There are many polymers that may be fit for us to make a polymer, solid polymer electrolyte, and we want to screen all of them. We will sample some from this large chemical space, and we will use traditional classical molecular dynamics to get some stored trajectories. These trajectories have a time step of femtosecond level. We downsample these trajectories, we coarse grain these systems, and we use them to train the machine learning simulator. So once we've get the machine learning simulator trained, we will screen the rest of the polymers in this large chemical space that we originally want to study. By using the machine learning simulator to simulate these novel systems for a very long time at a very efficient way by having nanosecond level timestamps and simulate the coarse grain configurations. And then from these long time trajectories that are coarse grain, we are still able to compute some long time properties that we care. Prudencio.
Yes, on the previous slide. Yeah. I was wondering if at some point you care about the back mapping from the coarse-grained level to the all-atomistic level.
Yeah, so back mapping, that's a very good question. There are many existing studies that are trying to investigate back mapping. So we did not consider back mapping in this work, but it's totally possible. And I think there are good scenarios where you may want to care about back mapping. For example, for proteins, you may want to study the folding and unfolding events at a coarse grain level, and then back map to get the full atomic resolutions. So that is compatible with other tools such as the protein ligand binding thing, where you do need atomic resolution thing to be able to compute some of these other scenarios or other modality of the data where you indeed need atomic resolution. It's not investigated in this paper, but it's a very relevant and very promising future avenue for this, I think. So I see some chats. Let me take a look. So the first question is how you get the trajectory simulated for the not coarse grain system. You just use classical molecular dynamics. So you already know how to simulate these systems. The only problem is the classical MD simulation is slow. You need very high computational costs to get many long trajectories for these systems. And I instead want to just use the classical MD to get me some data that I can train my machine learning model for. Then I use my machine learning model to efficiently get many long trajectories. The second question is, have you observed the dynamics of your spatially coarse grain system in comparison to atomistic simulations? Are they sufficiently more smooth that allows you to sample from them easier? So that is a good question. The length scale and the time scale of a molecular system is often coupled. So if you coarse grain spatially, it almost surely coarse grain temporally as well. So indeed, like you said, once you coarse grain, the entire energy landscape is smoothened a lot, which is exactly why it allows you to sample these systems more efficiently, like you said. It allows you to use long time steps once you coarse grain the system. And the downside is you don't know what you lose. You may lose the most important information you care. And that is something, for now, people often just experiment with a set of scales. But like you said, I think you're exactly right that it is the coarse graining that allows you to sample smoothly. And more specifically, it is very hard to recover the actual dynamics to 100%. especially for a system like this. So to answer your question, like how it compares to the atomistic simulation, I would say we see our simulation can recover many important properties. But more than that, whether it's so accurate, whether it can recover something else, it's hard to say. And it's certainly not the same as some of the recent existing work, like in PDE modeling, people often compute the MSE loss. That's certainly not the same as here, because once you coarse grain, you lose so much information, it's almost impossible to get very good MSE loss. But still, you may be able to recover many important properties. Maybe that's a very long answer. Sorry if that's not clear. You can maybe send another chat if it doesn't answer your question. So how slow is classical MD? Based on my experience, these calculations are actually quite fast, but they are just not accurate. Yeah, so it depends on what kind of system, right? If you're thinking about small molecule, then yes, they are quite fast. They are not accurate. But if you're thinking about these polymer electrolytes, they have like thousands of atoms. Each simulation, in this case, costs roughly 800 CPU hours. So you can parallelize this thing in maximum like 20 or 30 CPUs, and then it takes maybe like 1 to 2 days for each. So 1 to 2 days for each trajectory you want to screen over, and then you want to maybe screen 500 of them. So it really put a high bar on how much you can simulate with normal compute resources. But with the machine learning simulator, in this case, we can simulate one trajectory on average with less than 1 GPU hour. So it's always a question of how big of a system, how long simulation you want to simulate to talk about whether classical MD is fast enough or not. So there's always some room for you to improve. Okay, I hope that answers the questions. I'll just close the chat. And I will answer maybe another round of questions when we present a little further. Okay, so we've just talked about what are the ingredients in trying to accelerate these classical MD simulation that are large scale and long time scale. So put all these ingredients together, we get this model where we will embed this full atomic resolution system with a GNN to learn an atom embedding. And then we will coarse grain it to the coarse grain configurations like we discussed before. So this constitutes the pre-processing step of this model. Then with a short history of the coarse grain configuration, we summarize all the features within these k time steps, and we get a single feature representation of the system. And then we use a GNN to predict the next steps. We then compute the loss to against the actual next step to train this entire thing end to end. So here, all these blue blocks are trainable, and the red block is loss. Here we introduce this optional score GNN, which is diffusion model that can help you stabilize the dynamics. So basically, the simulation may become unstable if your simulation have some accumulated error. The system may go to an unphysical regime where nothing will be correct. So this paper, we investigated how we may use the diffusion model trying to fix errors in the simulation so that you can keep the system stable and simulate for a long time. So let's take a look at some of the case studies here. The first system we look at is the single chain polymer. So we are showing you an overlay of the fine-grained system and the coarse-grained beads here. So this is how this polymer chain move in the implicit solvent. So for this system, we're interested in the radius duration. So what does this mean? The square radius duration is defined as follows. It is the sort of a weighted average of the distance to the center mass. Here, di is the distance from the ith molecule, the ith particle to the center mass. So we see here from the left to right, is from has a low rigid duration to medium to high rigid duration. So you can see how a low rigid duration means the system is more compact, and high rigid duration means the system is more extended. So for different polymers, they have different such behavior. So you can sort of trying to distinguish one from the other to see how compact a polymer chain is. So we have many such polymers. They're composed of these backbone beads and pendant beads. So we can compose many different polymers, like the three you see here. And our goal is to really learn a very general simulator for all these polymers that are composed of these, that are made of these beads composition. Also, these polymers feature very different behavior in terms of how their rigid duration evolve through time. You can see like this on the top, that polymers tend to have a very high rigid duration and a high variance because it doesn't really wiggle that much. It doesn't really form into a like blob. And you can see the second polymer has a like a medium level rigid duration, and the third one has a very small rigid duration. And also in this paper, we're considering a generalization scenario where we train with some class 1 polymers, but we test on some class 2 polymers. So the difference is for class 1 polymers, it's a regular repetition of the 4 constitution units, while for class 2, it's a random shuffling of 4 constitution units. You can see in the circle area, there's some irregularity compared to the left. Also, we're trying to think about the regime where we're learning from short simulation and trying to simulate long trajectories. So during training, we have these trajectories have 50K tau long. And while we on the evaluation side, we have them as 5 million tau. So tau is the time unit for a reduced system because this is a conceptual system. It's not a real atomic system. And tau is the time unit in this case. So let's see. The first thing we want to check is whether our simulator can predict the mean rigid duration throughout time. So from the left-hand side, we see how, as we said, we have a different length for training versus test time simulation length. If we directly use the length of the training trajectory trying to predict the rigid duration, the mean rigid duration, this is the level of error we get. We get an R2. R-square statistics of 0.34. And we can use a supervised learning model trying to predict the mean rigid duration. And we see the error is also somewhat high. While the learn simulator is able to get the best performance out of all these 4 models. So since now we have a simulator, we can investigate things more than just trying to predict the mean rigid duration. We can now simulate this thing for a long time, and we can then try to investigate the distribution of the rigid duration. So here I'm showing you on the first row, I'm showing you the mean, not the mean, the distribution of the rigid duration of the prediction, which is blue, against the reference, which is orange. So you'll see the learn model actually recovers the distribution of the rigid duration for these 4 polymers very well. And on the second row, I'm showing you the pairwise distances between the ith and jth coarse-grained bead when you are averaging over the entire simulation. So you'll see again, the prediction matches the reference quite well in many cases. So the coarse-grained simulation is actually able to recover some of these distributional statistics of the original system. So I find this impressive because after all, you're reducing like 1,000 beads into only 10. Although your 10 bead is of course more dense because before they are just like atom type, and now the coarse-grained bead are learned with a very dense feature, and their evolution is parameterized by a very expressive graph neural nets. And further, which is I think is the sort of the most important results in this paper, is we can really try to recover some of the dynamical properties. So here, what I'm showing you is the autocorrelation function of the rigid duration, and the x-axis is time, and the y-axis is the autocorrelation. So this tends to decay to 0 for infinite time. However, the rate of this decay is different across polymers. And here we see the title for each of the plot says T Rg square is some time. So this time is the relaxation time for this polymer to decorrelate its radial duration. So basically, it's sort of saying how fast does this polymer sort of form into a blob and then extend back. So how fast does the radial duration change? So this method is able to recover some of these dynamical properties to a reasonable accuracy. We can also try to investigate the time independent. So this is the time lag independent component analysis. So we can visualize this. It's sort of like a PCA, but for time series. So you can see here the reference and the predicted surfaces are alike. So it's showing you these coarse-grained simulator is really able to recover some of the essence of the original dynamics. So the second system that we are investigating in this paper is the solid polymer electrolyte. So we are showing you this different granularity of the system here. So we have such a complicated system that are at atom scale, and they are composed with all these sort of polymers. And the system features this problem of we are trying to measure the diffusivity of the lithium ions. And if you're using a short time scale, you are really trying to measure the sort of the bouncing. You're in the so-called ballistic regime where the lithium ions are like bouncing around. So you don't really measure the true diffusivity if your simulation is not long enough. Here I'm plotting the estimated diffusivity. You're using a trajectory of this length, or if you use it longer. So this is a converging quantity when you use infinitely long trajectories. But like you see here, if you just have a short trajectory that are at the training trajectory length, in our case, which is 5 nanosecond, you're really not capturing the right diffusivity. And because of the nature of this the lithium ion diffusion, if you use a too short trajectory, you will almost always overestimate the lithium ion diffusivity in this case. So just to clarify, on the right-hand side, the rightmost plot, we are trying to measure the diffusivity of the lithium ions in the testing trajectories with simulations that are 50 nanosecond long. However, our training trajectories are only 5 nanosecond long. So in this case, we have all these different polymer molecules that are in this system. And I'm showing you here how these systems are being coarse-grained. We sort of still use the same graph clustering algorithm, trying to get the coarse-grained beta assignment and then coarse-grain the system. So we also have some TFSI ions, that is the negative ions in the systems. We coarse-grain them in a similar way. So here in this case, we coarse-grain every 7 to 8 atoms into a single bead. And in this case, we're interested, like we said, the diffusion of the lithium ions and also the radial distribution function. That is how the particles lay out structurally in this 3D space. So here we take a look at how well can we predict the diffusivity of the lithium ions. So here on the left-hand most, you'll see if you use a short trajectory, you almost always overestimate the lithium ion diffusivity. So you really need long enough trajectories to try to measure this quantity. And again, we can use some supervised learning method to try to predict the lithium ion diffusivity here. So again, it overestimates, despite we already try to accommodate this overestimation behavior, but with a limited amount of data, the supervised learning model still doesn't do well. And we also tried our model without the score model, like here the diffusion model refinement, and you'll see the system will go unphysical, and the predicted diffuse diffusivity are completely wrong in this case because the system goes unphysical and all the behavior are no longer realistic. While our full model, which has the score-based refinement, was able to predict the lithium ion diffusivity very well to an error that is reasonable enough that I can start to use this model to try to screen your polymer electrolyte candidates. So we also see this model can recover the radial distribution function reasonably well. And you'll see the red curves are with the model that doesn't have a diffusion model refinement. You'll see some unphysical stuff happening here. So here, the density around this very short radius basically means there are some atoms that shouldn't be too close, but they are too close. So it's some sort of colliding event between the particles. But this does not happen either in the ground truth nor in the simulation carried out by the model with a diffusion model refinement. And if we think about the time cost of these, our method really accelerates over classical MD by several orders of magnitude. So in this case, for the solid polymer electrolytes, each trajectory using classical MD will take like 800 CPU hours, where our method takes only 0.76 GPU hours. So to give a comparison between GPU and CPU, usually the same simulation, if you use it on GPU, is roughly 10 times faster. So using the classical MD, you may still need like 80 GPU hours to simulate the thing. So we are now trying to reason about what has happened in our investigation through this learned simulator. So the coarse-graining, the spatial-temporal coarse-graining is really a speed and accuracy trade-off. It's really hard to, basically there's no free lunch. If you want better speed, you will need to sacrifice something. And coarse-graining sacrifices the accuracy for speed. However, it may sacrifice it to an extent where the important long-time properties are still extractable from your coarse-grained system. However, we must note that this trade-off is very delicate and hard to characterize, like we just discussed about the coarse-grained level, at which granularity you want to preserve. The key quantities that are interested in really depends on what kind of phenomena you are trying to study. And this is sort of unavoidable when you are trying to study a more complex system. For example, the protein condensates or the virus capsid formation process. It's really hard if you don't try to use a coarse-grained method. It's almost impossible to study them. So despite all the sort of delicacy or difficulty in this process, it's still, I think, sort of the way to go to consider how we want to coarse-grain a system to preserve some quantities of interest. There are more recent work that tries to do a more direct approach, such as they would do differentiable simulation to directly adjust the parameter of a simulation by recovering this observable that I care. So in the end, it's a trade-off that we're thinking about when we're doing coarse-graining. And I think there are many promising avenues for this in the future in terms of how we want to better balance this trade-off. So I will answer a question here. Would you mind sharing a bit on the score GN block in your model architecture? So it's a very similar, if you know about like geodiff, although geodiff is equivariant. In this case, my model wasn't equivariant, but it's very similar where you just add noise to the particles, and then you let the model denoise such added noise. That's the training objective of the score GN. And during simulation, you will try to control a noise scale from which the score network denoise from. Basically, you're trying to see, okay, how much error does my predictor predicts, and then I will basically remove that noise using a score-based trained neural networks. So Prudential, I know the talk is meant to be 45 plus 15. I finished the presentation for the coarse-grain simulation. However, I still have some slides regarding metal organic framework design. So I'm happy to answer questions if we want to preserve the next 8 minutes for questions, or otherwise I can say a few words about how we have been using coarse-grain representation to design metal organic frameworks.
I think we can just post for question and yeah. So maybe like one thing that's fascinating for me is this figure how much you scale, at least the speed gain that you have. But as you said, like this come with a huge cost to accuracy, especially local accuracy. So have you studied like how to balance the speed with the accuracy, like while coarse-graining, especially I understand the thing for global properties, but there's a lot of this biomolecular system or large system also have a lot of local interaction that we are interested by. Mainly if you think about drug-target interaction, all the interaction are local and might be important to conserve some of that. Any thoughts?
Yeah, so that's a good question. There are more sort of fundamental grounded, theoretically grounded approach, such as coarse-grained force fields. So coarse-grained force field is somewhat very attractive in the sense that there has been theoretical results in how, if you train the coarse-grained force field with the force matching objective, you will be able to recover the ground truth free energy surface. So that is a very strong, it has very strong implications. That means this coarse-grained force field in convergence will indeed converge to the equilibrium distribution of the system. So like you said, am I still able to capture some of the like a reaction or like a dominant conformation and so on? The answer is if you're using a coarse-grained force field and you have infinite data, infinite compute, infinite expressive model, in convergence, you should be able to capture all those. Although in reality, it's a hard problem. But at least that offers you some theoretical guarantees on what you may be able to achieve. And so that is very nice. However, we just mentioned if you're using coarse-grained force field, then the speed is a concern. And but that at least is one stream of the work where you indeed can hold on to something that is giving you some idea about how well am I capturing the whole thing. And then maybe the next question is, if you're doing a coarse-grained force field, theory says you can recover the free energy surface. But does theory say anything about the dynamics? It only tells you the distribution will be correct, but it doesn't tell you anything about is the dynamics correct? Is the protein still fold and unfold with the right timescale? Usually the answer is no. So does the reaction still happens with the does the protein still unfold after like 100 nanosecond? No, the answer is no. The answer is if you do coarse-grained simulation, the answer will be wrong. So you do recover the free energy surface, but the dynamics will be wrong. And that is a very hard question to answer. I would say nobody knows how to answer that for now. And there are some very preliminary theoretical results. I would say very good, but still preliminary results exist. They are from actually the same group who does the proof for the coarse-grained force field convergence thing. They are at U Chicago, Greg Wolf's group. So they have some theoretical results on if you coarse-grain a liquid, you can somewhat preserve the timescale of the diffusion coefficient if you try to scale everything by blah, blah, blah. Yeah, so there are some theoretical results that tries to probe the question of what is being preserved, how am I supposed to preserve? But in general, it's a very hard question, and it's hard to answer them, and it's hard to consider when do we preserve them. So I would encourage everyone to think about these questions. It's a very hard question and would be very impactful if someone was able to solve it. But I guess to offer a starting point to think about this, I would really recommend the work from Greg Wolf's group at U Chicago. I'm sorry, it might be a very lengthy and maybe it does not fully answer your question.
It's perfect. Thank you so much.
Okay, Dennis, please unmute yourself.
Yes, thank you for a wonderful talk. It was really clear, but still I want to ask two questions. First, is about the sampling for training the coarse-grained and the time-integrated GNN that basically predicts next step. So I think there was a slide where you showed like end-to-end training. I think that one would probably be better. The next one, I think, yes, please. So you essentially here input some kind of coarse-grained system into your GNN and predict its time evolution during some interval of time. And my question is, how do you choose this interval of time? Because it seems like if you do like uniform sampling or stochastic sampling, it can act differently.
You're totally right. So unfortunately, in this work, it's still hyperparameter tuning. And it's in general a hard question to think about what's the right timescale. So if you're using a longer DT, you're of course smoothing out the finer frequency, like the finer details of the dynamics. So if you use a longer DT, you give up more information. You're left with something simpler, and you're left with this simpler thing that is easier to learn, and they lose information. And there's a delicate balance between what you lose, what you keep, what you're able to learn, and what in the end you extract from these trajectories. So this may be an unsatisfying solution right now that we're just screening the few hyperparameters and see whichever works the best. But I would say this question is sort of similar to the entire coarse-graining theoretical perspectives on what is the right scale, what is the best scale for this problem.
I see.
I can't really answer this question. Yeah,
I see. And the second question is much more concrete. I don't really understand what the embedding GNN is doing here, because for me it seems that coarse-graining is like not a learnable process, right? It's just a clustering algorithm.
Yes, so coarse-graining is not learnable. However, if you look at these atoms here,
I see. I understand. So you're coarse-graining the node features, basically.
Yes. So the embedding GNN tries to learn the node feature in this level. So the embedding GNN will let you be able to capture some local environments for each of the atom in this case, so that, for example, this red bead and that red bead are different. So the embedding GNN will be able to learn that.
Yes, and it is trained based on the loss that is showed on the previous slides in the end. So essentially, I'm just a little bit confused how the gradient is propagating. So if the embedding GNN is first applied to, let's say, 2 time samples from the atomistic trajectory, and then if this is an end-to-end system, then you coarse-grain the atomistic trajectories differentiably, and then you pass it into your dynamics GNN. You produce coarse-grained structure at the next step, time step, and then you propagate the loss back to the like compared to the atomistic projection at the same time.
Yes, because the coarse-grained process is still differentiable, right? It's really just some sum and mean and weighted sum of the atom features. So all this process is differentiable.
Yeah, I see. But then it's even more dependent on how you choose your time sampling. But yeah,
of course.
I see. Thank you. Thank you.
Yeah. So it is indeed a dedicated process that is somewhat not too robust to the hyperparameters. Yeah, we tried our best. Okay, thank you for your question, Dennis. Another question from Lena. Could you share the name of the group that work on these theoretical results? Sure. So Professor Gregory Wolf, he's the professor that leads these efforts.
Perfect. Thank you so much, Shang, for the great talk. Uh, I think with almost no time left, I think we can stop for here today, and we will, yeah, maybe find another opportunity to share the remaining of the slide with the audience, or yeah, through the Slack or other channels.
Sure, sure. Yeah. Maybe just one shameless uh, advertisement is the new paper. In the new paper, we also use coarse-graining approach to uh, generate some MOF structures. If you know what MOF is, it's like some complicated metal and organic molecules they form together as a crystal. So if you're interested, take a look.
Okay, cool. Perfect.